This is the first lesson in this course on fluid mechanics in medicine, and the topic is density and specific gravity. The learning objective of this lesson is to have an understanding of the physical property of density and to know the meaning of specific gravity, particularly as it relates to urinalysis. I mentioned in the introduction to this course that I was assuming no prior knowledge of fluids. If this topic is old news to you from high school science class, feel free to continue on to the next one. So here we have a sealed jar of water, which is the prototypical fluid that I'll be referring back to many times during this course. Before I jump into density, I first want to talk about what makes something a fluid. A fluid is a substance that continually and smoothly deforms when shear stress is applied to it. What exactly does that mean? Fluids flow when acted on by a force, just like water flows downhill when acted on by gravity. That's it. In common usage, we tend to think of fluids and liquids as synonyms, but in science they're not. Fluids encompass more than just liquids, but also gases, as well as something called plasma. We won't talk any more about plasma, but liquids and gases share many of the same physical properties, which are governed by the same laws. So except at times I state otherwise, everything I talk about in this lesson and this course as a whole applies to both liquids and gases. Now let's talk density. I'm sure all of you have some idea what density means. It's a measure of how much stuff is squeezed into how large a space. For example, a steel bar is very dense, while styrofoam is not. When it comes to fluids, there are a number of properties that determine their density. You'll notice that the universal symbol for density is this round lowercase p that's actually the Greek letter rho. The first property that determines density is the mass of the fluid's constituent atoms or molecules. In general, the greater the molecular mass, the more dense the substance is. Remember that despite its appearance to the contrary, water is not some homogeneous uniform substance down to the smallest of scales. Rather, it's composed of individual molecules, each containing one oxygen atom and two hydrogen atoms. These molecules are moving every which way, some faster, some slower. Interestingly, the fact that water is a liquid at room temperature, and thus relatively dense for a fluid, is a bit of a fluke. After all, its relative molecular mass of 18 is higher than many gases, such as 16 for oxygen and 15 for nitrogen, which have densities that are much, much lower. The reason water is a liquid, and why it's relatively dense, is the large contribution of something called intermolecular forces, including something called hydrogen bonds, that may sound vaguely familiar from high school chemistry. Intermolecular forces are essentially electromagnetic interactions between adjacent molecules, or between adjacent parts of the same molecule, that aren't strong enough to be considered a true chemical bond. Other determinants of density include the presence of dissolved compounds, as dissolving something like salt or sugar in water tends to impact the mass of the liquid much more than it changes its volume. Temperature also impacts density, with higher temperatures leading to lower densities and lower temperatures leading to higher ones. And finally, there's pressure. For gases, higher pressure leads to higher densities, which might seem obvious when you think about it. Very importantly, however, elementary fluid mechanics assumes that liquids are non-compressible. That is, pressure does not affect the density of liquids. In reality, that isn't exactly true, but the effect is so small that unless pressures are truly enormous, it can be ignored. What range exists for the densities of commonly encountered fluids? Since temperature and pressure can impact fluid density, as just discussed, technically the temperature and pressure should be defined when discussing a substance's density. We commonly refer to something called standard temperature and pressure, or STP. This is defined as 0 degrees Celsius and a pressure of 100 kilopascals. Don't worry yet about what a kilopascal is. We'll get to it in a few videos. So at standard temperature and pressure, the density of water is 1,000 kilograms per cubic meter, which sounds really high until you realize that a cubic meter is actually quite a bit of space. That's the same volume as 500 2-liter bottles of soda, and that's going to be pretty heavy. And if you're thinking what a convenient coincidence it is for water's density to be such a nice round number, it's not a coincidence at all. The unit of measurement of a kilogram is actually defined based on the density of water, which results in a relationship that's critical to remember. 1 liter of water is 1 kilogram in mass by definition. Another commonly encountered fluid is oxygen. The density of oxygen is tiny, 1.43 kilograms per cubic meter. And finally, at the other end of the density spectrum is the densest of all liquids, mercury, at a whopping 13,500 kilograms per cubic meter. The density of mercury is largely a consequence of its atomic mass of 200. The explanation as to why something as dense as mercury is a liquid and not a solid requires quantum physics, and thus I won't get into it here. So how does one calculate density? The equation is one of the easiest to remember and understand in all of physics. Density, which is usually expressed as kilograms per cubic meter, is equal to the mass of a fluid over its volume. Very intuitive. And you may already know that the above calculation also happens to be true for solids. Let's do a super simple example. Suppose the jar shown here weighs 0.2 kilograms when empty and currently weighs 1.4 kilograms. What volume of water does it currently hold? As I just said, density equals mass divided by volume. Plug in the numbers. 1,000 equals 1.4 minus 0.2 divided by V for volume. Solving for V, we get a volume of 0.0012 cubic meters, which is equal to 1.2 liters. Moving on from density, let's discuss the concept of specific gravity. Specific gravity refers to the ratio of the density of a substance compared to that of water. Mathematically, this means specific gravity, often abbreviated capital S, capital G, equals the density of the liquid divided by the density of water. Yet another super easy equation. So if the density of ethanol is 789 kilograms per cubic meter, what is its specific gravity? 789 divided by 1,000 is 0.789. It's so simple it seems silly for someone to have bothered defining the concept. One important aspect of specific gravity, however, that may seem obvious is that liquids with a specific gravity less than 1 float above water, and those with a specific gravity greater than 1 sink beneath water. How is this used in medicine? Let's take a urine sample from a patient. I'm sorry to make this the first medical example of this course, but that's just how the topics worked out. The specific gravity of urine is a measure of its concentration, or more accurately, a surrogate for its concentration. When one sends a urine sample to the hospital lab, typically within an hour or so, a urinalysis report is available that looks something like this. There's a list of physical attributes of the urine, as well as some substances that may or may not be present. The presence of certain substances may suggest underlying kidney or bladder disease. For example, in this case, the trace protein suggests early kidney dysfunction. What we're more interested in today, however, is this, the specific gravity. The normal range of the specific gravity of urine varies ever so slightly from one lab to another, but is usually about 1.001 to 1.035. In other words, most urine is ever so slightly more dense than water, which makes sense since urine is essentially a solution in which electrolytes and a compound called urea are dissolved in water, increasing the liquid's mass but having little impact on volume. Depending upon the specific clinical scenario, different values for the specific gravity may lead one to different conclusions about the patient's current medical condition. For example, if the specific gravity of the urine approaches the upper limit of normal, as in this case, it implies that the patient may not have adequate blood flow to the kidneys, usually due to either dehydration or heart failure. This will correspond with a urine that is very dark yellow in color. Conversely, if the specific gravity reaches or even exceeds the lower limit of normal, it implies one of three things. The patient may be experiencing an impulsive consumption of water, which is a psychiatric condition called primary polydipsia. The patient's kidneys may be unable to concentrate the urine, a condition called diabetes insipidus, not to be confused with the other diabetes that's associated with blood sugar. Or last, the patient has intentionally diluted the urine with water after micturition. Why would someone want to do that? Trying to pass a drug screen. Does it work? It can, but it's impossible for an individual to guess at how much water to add in order to adequately dilute the urine to make the drug undetectable without making it so dilute as to become physiologically impossible. Not taking illicit drugs is a much more reliable means to pass a urine drug test. So that's it for density and specific gravity. The next lesson will cover buoyancy.